So today we're going to be estimating values. Now this is going to be an example of how we're going to go through class this year. So this should be a review for most of you. Sometimes the value of a number is not obvious and we have to perform a few steps to uncover what it actually is. And these steps are going to be what we call an algorithm. Now our arithmetic algorithm is we're going to do step 1 is we're going to identify any groups of parentheses or brackets. E is we're going to identify any exponents. M and D are we going to identify multiplication, division. A, S is going to be addition and subtraction. And you may recognize that as PEMDAS. Little did you know that you were performing algorithms at a very early age. This isn't something strictly isolated for computer science. We're going to go through this series of steps and solve these things. So let's take a look at number 1. Number 1, this is a value, albeit in algebra, what we're going to do is we're going to perform a series of steps in order to figure out what this value actually is. Because we don't like thinking of a value of 2 more than 6. We like thinking of a value of 8. And now, albeit some of these are very simple, some of these we're just looking at the new way we're going to be writing the expression. If we take 12 divided by 3, that's going to be a fraction. Normally you're used to seeing something like 12 divided by 3. This is no longer going to be the case. We're not going to write it like that anymore. Anytime you see division, we're going to represent it by writing a fraction. So we know 12 divided by 3, well 3 fits evenly into 12 4 times. And likewise, we might get something like this where we say 2 parenthesis 4 close parenthesis. Now this you might have seen in old school as 2 times 4. We're going to get rid of this style of writing now because that x later on in this course is going to represent a variable. We don't want to confuse the operation with the variable. So we're either going to represent it with a set of parentheses, and we know this is an assumed multiplication, or if you really want to, you can put a dot between the two. And that is our new symbol for multiplication. So we know 2 times 4 is going to get us 8. And as we work our way down, we're just going to add more of these steps as we go. 3, with 3 in the upper right diagonal, this is to the power of 3, or 3 cubed. The way that we're going to read this is we're going to write 3 times itself 3 times. So 3 times itself once, times itself twice, times itself 3 times. So now I know that I'm going to say I covered my exponent, I just have multiplication and division to handle next. 3 by 3 gives me 9. I'm going to carry down this other 3. 9 by 3 gives me 27. Boom. When we look at something like this, we know the fact that parentheses is going to come before exponents. So I'm going to go inside and do what's inside the parentheses first. 17 minus 5. That's going to give me a 12. 12 squared. Now, albeit I still have parentheses, there's nothing left to do inside. It's just a number. So now I can move on to the next step of exponents. 12, I know that this is going to be written out as 12 times itself 2 times. So I'm going to write 12 times 12, which if we remember, 12 and 12, 2 by 2 is 4, 1 by 2 is 2, hold my 0, 1 by 2 is 2, and 1 by 1 is 1. Add these together, 4, 4, 1, 144. Oh, there we go. And now, sometimes we may not see parentheses, but they're implied. If I look at this 2 plus 10 divided by 4, I'd want to do multiplication and division first because I see this big division sign. But what we know with fractions, there's always an assumed set of parentheses around the numerator and the denominator. And this will help us figure out how to solve this. If I take 2 plus 10, that's going to give me a 12 divided by 4. And then it's solved very similar to the question 3. 4 fits into 12 3 times evenly because I'm dividing 12 by 4. This is how we show division. So let's move on to some of the other problems. With, let's say, this one. With this one, I'm going to go into my parentheses and see what I can do inside of it. I know inside of it, there's no additional parentheses, but there is exponents. So I know I'm going to end up with a 2 times 2 times 2 minus 1 times 2. And so inside the parentheses, I'm going to perform the set of operations. 2 times 2 is 4, times 2 is 8. Be careful you don't write 6. A common mistake is that people add these things together. They're like, okay, I'm adding 2 3 times. We're not adding, we're multiplying. So my 8 times 1 gives me 7. 7 times 2 is going to give me a 14. Because remember, when there's a set of parentheses and that is not an exponent, that's not a squared, that's a times 2, we're assuming that operation is multiplication. And now the last thing that we're going to look at is this one right here. So we're going to look at this one. We have a 4 plus 6 divided by 2 plus 3. Again, it looks like we'd have to divide maybe 4 by 2 and 6 by 3. That's not the case. We remember the fact that any numerator and denominator has an implied set of parentheses. So we're going to go into the parentheses step and do that first. I know 4 plus 6 is going to get me 10. 2 plus 3 is going to get me a 5. So now that I've gotten rid of the operations inside the parentheses, now I can go ahead and divide 10 by 5, which I know is going to equal 2. So this is the real number system. What we're looking at here is we have 5 different types of numbers, and we're going to introduce a 6th type later on in the year. And this whole thing is called the hierarchy of classification. What we start with is we start with the real numbers. And inside the real numbers are 2 different types of numbers, irrational and rational. Rational contains integers, integers contains whole numbers, and whole numbers contain natural numbers. And so what we're going to start with is we're going to start with the natural numbers. These were the first numbers that were invented. These are things that you can see in nature, like 1, 2, 3, so on and so forth. The idea being that if you're out hunting, you see 1 deer, you see 2 deer, you see 3 deer. Later on, as we get more developed, we invent a placeholder for when you walk out and you see no deer. Previously, it was just there's no deer. Well, how do I account for that? Well, I include the number 0. Now, whole numbers also include all natural numbers and the number 0. After that, we move on with the number system a little farther. We develop the concept of currency, and we say, hey, it's possible to have 3 deers. It's possible to say if you have 3 and you owe me 6, well, I know that in your pocket you have 0 deers, but in the fact that the negative numbers come into play here. And that you would technically owe me 3 deers. Not only do you have nothing in your pocket, but the next 3 go somewhere else. We extend that even further. Once we start dividing things, we get the rational decimals or the rational fractions. The base word here is ratio. So if I have a repeating decimal, let's say 1/3, that's a fraction. I can write that decimal as 0.3 repeating. I know it comes after that 3, another 3, and another 3, and another 3, all the way so on and so forth. Both of these are rational. I can also get something like 0.4545, and if the 45 is repeating, it doesn't need to be the same number. That is a rational number. The last one could be anything as easy as, let's say, 4/5. That's simply a 0.8. All of these are rational numbers of different sorts. 4/5, 1/3, 0.3 repeating, or 0.45 repeating, 0.8. On the other side, if it's not a constant pattern or terminating pattern, we get irrational numbers. These are things that you might have seen like 3.14, 15, 92, ... You might recognize that number as pi. There's no pattern to the numbers. They're seemingly at random. Another way that we see that is non-regular roots. Something like the square root of 5. The square root of 5 has no pattern. It's somewhere between the square root of 4 and the square root of 9. So it's somewhere between 2 and 3, but that number itself is non-repeating. So what we're going to do is we're going to classify the following numbers. The square root of 3 is going to be not something that we can figure out because it's not the square root of 1, it's not the square root of 4, it's something in between. It's a non-regular root. So we would call this irrational. 1/2 is rational. It's a ratio of two numbers. If we move over, the square root of 4. Well, I know the square root of 4 is equivalent to 2. 2 is my most basic of numbers. It's natural, so we know it's natural. But if it's natural, it's also contained within whole, which is also contained within integer, which is also contained within rational. So 2 is all of these. It's every single category going on up. We could also include real, but now remember, we're including the real number system, so all of these answers are assumed to be real. -7, well, it's not natural, it's not whole. It is an integer though. And by definition, if it's an integer, it's also contained within the rational numbers. The last one right here is -2/5. It's not natural, it's not whole, it's not an integer, but it is a ratio of two other numbers. So I know this one's going to be rational. And then we can move on to the next topic that we have. We have open and closed systems. Now, open and closed systems just means, can we create something new from something that we already have? Can we create a higher level of number using some basic arithmetic? If I can't create anything new, it's considered closed. So let's try out a few examples. The first one, I have 5 and 7 with addition being the arithmetic we're using. 5 is a natural number, 7 is a natural number. And by definition, it is every single one of these. But I'm seeing if I can't take a natural number and create something a little higher. Can I create a whole number? Can I create an integer? Can I create some sort of repeating decimal or fraction? Well, if I take 5 and 7, natural, that makes 12, which is also natural. There's nothing new created here. I stayed within my same area, so therefore this system is closed. And what we're doing at the bottom of this is we're saying, hey, natural numbers are closed under addition. So I'm closing off the box. A counterexample would be if I take 3, a natural number, and 4, a natural number, and I subtract the two, I'll get -1, which is an integer. I took a natural number and I made something higher. I made something more complex, which means that this system is open under subtraction. And so what I'll say is I'll say open, and my example would be 3 minus 4 is -1. I took two naturals through subtraction and made something different. So on and so forth. You'll see how the table's being made as we go along. Other examples of open and closed systems are looking at some literal examples. If I have two ducks, duck and a female duck, I need to fix that typo, but we're gonna go ahead with this. If I have two ducks, a male duck and a female duck, if they were to breed and make an offspring, what would they make? Would they make a cat? Would they make a Tyrannosaurus Rex? No, they'd probably make another duck. So if they make another duck, we're going to call that system closed. There's no way we can have two ducks and make anything other than a duck. Now, You might ask yourself about evolution and things of that nature, that eventually a duck will morph into something else. And yes, that is the long-term example, but as of right now, we're just looking at these two ducks, and the discernible baby duck is no more different than the two parents on a basic level. If we move forward, if I have a Russian mother and a Russian father, what type of baby will they produce? Well, your answer probably is going to be, well, a Russian baby. And 9 times out of 10, you'd be accurate. But what happens if that Russian mother and Russian father have emigrated to another country? Let's say they emigrate to Britain. They emigrate to the United Kingdom. So that Russian mother and Russian father, their baby has dual citizenship. That is a English and a Russian baby. We've created something else. So this system is open. Likewise, another look, if I have a brown dog and another brown dog, their offspring most likely is going to be brown puppies. But I'm sure everybody has known somebody who's bred 2 brown dogs and they get that token spotted dog, that token gray dog, that token black dog. So this is another example of an open system, because you might get a gray, you might get a spotted, you might get a white puppy. Now the chances are it's probably going to be brown, but you have examples of something else, something open. And the last example are the mother and the father with the flu. Again, this is another example of an open system, because what we're looking at here is, albeit that mother and the father, when they have the baby, that baby most likely is going to be healthy, but seeing as its mother and its father both have the flu, it's most likely going to get sick very quickly. There's a chance that it may not. There's a chance that it may come out and immediately get the flu, so there's no discernible difference. The idea is that a sick mother and a sick father can produce something other than a sick baby. So those are open and closed systems. Again, if we take a few more examples, let's take a look at 2 integers. If I take 2 integers, let's say a -2 and a -3, and multiply them together, I'm going to get a +12, which is not a more complex number, it is a simpler number. So, no. What about different types of integers? How about -3 and 0? Well, that gives me 0. That's again a simpler type of number. It's not more complex. And no matter what 2 numbers we try and multiply together, if they are integers, we'll get nothing other than an integer or something lower. Unlike with division, if I take 2 integers, let's say -1 divided by -2, I'll get a +1/2, which is a rational number. The system is open under division. I can make something, I was multiplying whole numbers, oh well. Works the same with integers. So I can get something a little larger. I can take 0 divided by 1. I can take 1 divided by 3. I can take 1 divided by 0, and I'll get something that is either rational or undefined in that case, but I get something more complex. So let's say whole numbers. Boom.